Welcome to this video. Here we are going to discuss about cache memories in memory system. What is cache memory? It's for increasing the speed of the computation. It's a memory kept in between the processor and the main memory. Here processor wants to access anything, then it has to go to that memory. It will take more time. Instead, whatever things available, see this little bit of things may be loaded into that cache memory. If the processor needs the instruction or data, that can be referred in the cache memory before seeing in main memory. If it's available, it can access it in less time. If it's not available, then it has to go to the main memory. So the cache memory for improving the speed of the computation. Okay, the cache memory is an architectural arrangement which makes the main memory appear faster to the processor than it really is. But the thing is, how do you access this cache memory? Okay, the cache memory is based on the property of computer program called locality of reference. Okay, there are two things. One is temporal locality of reference, spatial locality of reference. Okay, what is locality of reference? The analysis of program indicates that many instructions in localized areas of a program are executed repeatedly during some period of time, while the others are accessed relatively less frequently. So temporal locality of reference means the recently executed instruction is likely to be executed again and again. So this is going to be kept in the cache memory because this will be used in processor later. Then second thing is about spatial locality of reference. That means the instruction which is close to the recently used addresses will be used again. So this may be placed in that cache memory. So how do you keep the data or instruction in that cache memory? Based on the two things, that is called locality of reference, either temporal locality of reference or spatial locality of reference. Temporal means the instruction which is executed will be used again, that will be kept in that cache memory. Or spatial locality of references, the instruction which is close to the instruction which is recently used will be kept in that cache memory. Then the cache memory, it's a processor issues a read request. A block of words is transferred from the main memory to the cache memory, and one word at a time. The subsequent reference to the data in this block of words are found in the cache. For example, here we have a one block of data. Okay, the one block of data will be transferred to this cache memory, not one word or something, not like that. One word of words will be transferred to the cache memory for reference. So at any given time, only some blocks of main memory are held in the cache. Which blocks or in the main memory or cache determined by the mapping function. There are three types of mapping function: direct, associate, set associate. So based on then, how do you get the block of data from the cache memory, and that will be placed in the main memory to cache memory based on the mapping function. There are three mapping functions we'll discuss. Then when the cache is full, see this main memory capacity is higher than the cache memory, so we cannot place everything in this cache, only little. Okay, only a less amount of data will be placed in the cache when compared to main memory. So the thing is, how do you, when the cache is full, then how do you replace? No, you want a new block which is not available in the cache memory, then how do you replace? We have a replacement algorithm. We'll see, discuss about first in first out, then least recently used, we'll discuss. Okay, so the mapping function for mapping, okay, placing that word, blocks of word into that cache memory where you want to place it in the cache memory. And replacement algorithm for when the cache is full, then how do you remove that particular block from the cache memory for adding new block to the cache memory. Then what is cache miss, cache hit? Okay, the cache hit means the processor wants to access the data. First, it is going to see the data in the cache memory. If it is available in the cache memory, it is called cache hit. Okay, the existence of a cache is transferred to the processor. It's going to be read or write. Okay, then obtain, read hit in the sense data is obtained from the cache. The browser wants to access some data. It's available in the cache. It can access it from the cache instead of going to that main memory. It's called read hit. Write in the sense cache has replica of content of main memory. Okay, the content of cache and the main memory may be updated simultaneously. The thing is, the content, okay, you won't write the content from the cache to that. The processor wants to write some data. Okay, then what happened? First, it has to update that in cache and this main memory. Okay, the original memory is a main memory, the cache memory for reducing the speed. So, reducing that time to access the data, increasing the speed. So, what happened here? We have to update. For example, one particular block A is available in cache as well as this main memory. Now any updation in this block A should be reflected in the cache memory block A and this main memory block A. Okay, so what happened if that content, see the content of the cache and the main memory may be updated simultaneously. The processor wants to update some data in block A. The block A is available in cache as well as this main memory. So it has to update the data in the block A, both cache and the main memory. It is called write through protocol. The second is called write back protocol or copy back protocol. What happens? The processor wants to update some data in block A. The block A is available in cache as well as this main memory, but the process is going to update only that cache cache memory data of that block A. Then this will be reflected when the block is going to be removed from the cache. That time only it is going to be reflected in that main memory is called write back or copy back protocol. Cache miss. If the data is not present in the cache, then it's called read miss or write miss. Okay, the read miss in the sense the blocks of word containing this is requested word transfer from the memory. After the block of transferred, the desired word is forwarded to the processor. Actually, the thing is it is trying to access a particular word, it's not available. Okay, then you can go for this write through protocol and load through or early restart protocols. Then we have one more thing called cache coherence problem. What happens if your data in the disk and main memory changes and the write back protocol is being used? In this case, the data in the cache may also have changed and is indicated by the dirty bit. Okay, you are updating one particular data in the cache memory, not updated in that main memory. We can go for having some bit called dirty bit. Okay, this will be updated if any changes in that data. The copies of data in the cache and the main memory are different, then it's called cache coherence problem. That's why I said if processor is going to update particular data in the block A in cache, not updated in that main memory, then we have a different data, different values for the particular data. It's called cache coherence problem. How do you overcome this one? One option is to force write back before the main memory is updated from the disk. So we have to go for following that write back or write through protocol. Second thing is we can go for using this valid bit. Okay, the block contains a valid bit, then bit is set to 1 or 0. At the beginning it is set to 0. Whenever the data of the particular block is updated, this is set to 1. So what happens when you are going to remove that block from the cache memory? If the bit is equal to 1 means some data is updated in that particular block, so that should be reflected in the main memory. So the valid bit is equal to 1 means some data in the block is modified, so update this in the main memory, then remove it. This purpose we are going to use the valid bit. This is one way to solve the cache coherence problem. Then mapping functions. The mapping function in the sense how do you place that block of data from main memory into cache memory? Where will you place it? This will be determined by the mapping functions. For example, consider a cache consists of 128 blocks of 16 words and the main memory consists of 2048 words. Okay, then you can go for having number of words and blocks. There are three types of mapping: direct mapping, associate mapping, and set associate mapping. What is direct mapping? The direct mapping, the block, see here this is your main memory. Okay, this is a main memory and this is a cache memory. Okay, then here we have, here we have 128 blocks from 0 to 127. Here we have 0 to 4095, so totally 4096 blocks. Okay, so here we have 128, here 4098. we cannot keep all this in the main memory. So only few blocks can be placed for the reference of processor. So thing is, how do you place it? The direct mapping is following a formula called J modulo 128. This 128 is nothing but number of blocks in the cache memory. So here you want to place this, and for example, you want to place this block 129 means the J is nothing but 129 modulo 128, then you'll get 1. So this will be placed in the block 1. Then you want to place the block 0. Block 0 you want to place means apply 0 modulo 128, you'll get 0. You can place it here. Okay, this way the direct mapping, the blocks in the main memory can be placed in the cache memory. Okay, here we are using, how do you go for using this main memory address? Okay, we have 4006 blocks. Each blocks has some number of words, right? So here what happened, the totally we have around 16 bits of memory address, 2 power 16 locations are there in the memory. So here this can split this into tag 5, block 7, word 4. The word is nothing but 4. So each block you have 4. That is 2 power 4, 16 words. Okay, in the 16 words, which word you want to access? This will be represented using this word. The lower 4 bits determine the 16 words in a block. So each block you have 16 words. 16 the sense 2 power 4. Okay, then you can access 4, you can give 4 bits for representing which word you want to access from the block. Then this 7 for, okay, there are 128 blocks. So here 2 parts are 128. Which block you are going to access from this? Okay, see in which block, block 0 or 1, which block you want to access, that will be represented using this block 7 bits. Then here tag for which there are 32. Okay, 32 tags, which tag you want to access. Okay, so this about here 12 bits for representing direct mapping. So direct mapping, here you want to place one particular block, then you have to go to that formula, the block number modulo 128, there you are going to place it. But associate mappings in the problem of direct mapping is, here sometimes it results same number block like 0, 128 like that, the same block is used, remaining blocks are not used. To avoid this we can go for associate mapping. Okay, here memory block can be placed into that cache, any cache position which is free. Okay, there are two things in that 16 bits of address. The 4 for accessing that particular word in that block. Then tag for, here we have 128 tags. The only tag number will be given using the 12 bits. Okay, then use this tag and word for finding the particular block. Then set associate memory. It's a combination of both direct and associate mapping. So here the thing is, we are going to use this blocks. Okay, here for example we can make this 2 blocks or 1 set. Okay, 2 blocks or 1 set. In this case, if I'm going to place 0 and 128, then apply the formula J modulo 128. So 0 modulo 128, I want to place the 0 block. Then 0 modulo 128, I will get this block 0. Again 128 modulo 128, I will get block 0. So I cannot place the same. But the same set I can place block 0 and block 128 in the same set. So here what about the addressing? The 4 for finding that which word you want to access in the block, and set for which set. Okay, the which set you want to access, because there are, suppose you have 128 blocks means there are 64 sets, right? 64 can be represented using 2 power 6, right? So here you need which set you want to access, the set which tag you want to access. Okay, so this is the way we are going to access it, associate mapping. It's a combination of both associate and direct mapping. This is a way block will be placed in that cache memory. Then if the cache is full, you want to remove one block from the cache, which is going to be replaced. You can go for different methods. Least recently used, first in first out, least frequently used, random. We'll see only two here. The first in first out method. The first in first out method, we can say that cache blocks in terms of pages. Okay, first what happened, assume these are all the pages you want to place. This 7, 0, then 1, these are the pages. Now we have only 3 blocks. Assume only 3 blocks. Then you have to place, you have to see whether 7 is there or not. No, 7 is not there. Place it here. Now you are going to see one particular page is available in that block. In the cache, it's available. Then hit occurs. Then if it is, yeah, it's not available, then page fault occurs. So what is page fault? You are trying to find the particular block or page in that cache. It's available. Hit, it's not available, page fault. So what happened? You are trying to place 7 here. It's not available. So place it 7. One page fault occurs. Again 0, you can place it here. First come first served, right? Then 1, you can place it here. Okay, then what happened? Now 2 comes, the cache is full. Where will you keep it? Which one come first? That is going to be replaced. So 7 come first. Now replace 7 and place 2. Then 0 comes. The 0 is already available. So hit occurs. So 1 hit occurs. Then again the frame is 201. You want to place 3. Then which is coming first? 3, 0. So replace 0 and 3, 1. Then 0 is not there. Place it 0 here and 4. So keep on moving like this. Okay. You are placing this 2 here. Then you are placing 3 here. So which has come first, that is going to be replaced first. Now 0, 2 and 2 is available. So hit occurs. Second hit. Then place 1. Okay. The this is going to place 1 and this 2 is already there. So keep on moving. Here its hit occurs. So here you have to count the page fault in the terms of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is 15 page fault occurs. Then hit 1, 2, 3. Okay, here this first come first served first out algorithm, it's having more uh, page fault. It's not that much efficient. So advantages are it is easy to understand. It is very easy to implement. But drawback is it's very old method and it is having more page fault. Then least recently used method. What is least recently used method? Here you are going to find which is not used for longer period, that is going to be replaced. Again take the same reference string. It is 7, 0, 1. Okay. In this you have assumed 3 blocks in the cache. Where will you place it? First 7 you are going to search. It's not available. So place 7 here. Then 0 here. 1. Now the cache is full. Now where will you place 2? Which is not used to 701, which is not used for longer period 7. So just replace this 7 and put 2. 0 is available, 1 hit occurs. Then you want to place 3, right? 3 which is not being used for longer period, 1 or 2, because 0 is recently referred. So we cannot replace. Consider 2 or 1, which came first? 1. So replace this 1. And 0 is already available. Hit occurs. Now you want to place 4. Where will you place 4? 0 is referred recently. 3 is also referred recently. 2 is only referred late previous when compared to 0 and 3. So replace 2. Then 2 is again among this 0 and 3 which is not referred for longer period. 2. Then 3, 0, 3 here hit occurs. Okay. So this is a way we are going to calculate. We are going to place that particular block in that cache memory. Okay. So here number of page fault 13, number of page hit 66. Okay. This is about cache memory. So cache memory for improving the speed of the computation. Then LRU page replacement algorithm is quite efficient. Then implementation is difficult, but it's very tough to track which is not recently used. Okay, thank you.